In this video, we're going to be talking about hypothesis testing in the bivariate regression model. One thing that we've talked about before is that if we have a set of random variables that are normally distributed, any linear combination of those normally distributed random variables will themselves be normally distributed. If the error terms in our regression equation are normally distributed, then we know that since the estimated intercept and slope are linear combinations of those error terms, then the parameter estimates beta hat 0 and beta hat 1 will also be normally distributed. And we've already determined that the mean of each of the parameters is a population parameter because we know the estimators are unbiased. A proof of that is contained in the appendices in the text. We also derived the variances of these. So the variance of beta hat 0, the intercept estimator, is sigma squared times x bar squared over the sum of the x minus x bar quantity squared plus 1 over n, while beta hat 1 is distributed normally with a mean of beta 1 and a variance of sigma squared divided by the sum of the squared deviations of x from its mean. However, even if the error terms are not normally distributed, the central limit theorem suggests that the intercept and slope estimators will converge to a normal distribution as the size of the sample approaches infinity, as long as the underlying distributions have a constant mean and a finite variance. So in a large sample, we can treat the parameter estimators for beta hat 0 and beta hat 1 as normal, even if the underlying error terms are not normally distributed. So when we're dealing with large samples, in practice samples of over 100 or so, we can pretty safely assume that the normal distribution will be a pretty good approximation to whatever the underlying distribution is. And when we deal with distributions of 1,000 or more, we can pretty much assume that the normal distribution will apply. So if the parameter estimates are normally distributed, we can convert from a normally distributed random variable to a standardized normal variable by subtracting the expected value and dividing by the standard deviation of the variable. In other words, using a z transformation that's on the screen. So for either the intercept or the slope parameter, if you take your estimated parameter and you subtract the true value of the parameter and you divide by the standard deviation of the parameter estimator, that will be distributed as a normal distribution with a mean of 0 and a variance of 1. Since we don't know the true value of sigma, the standard deviation of the error terms, we instead replace the z-score with a t-statistic, which looks very similar except we're dividing through by the estimated standard error of the parameter beta hat 0 or beta hat 1. This applies to either. As we've talked about, that's going to be distributed as a t-distribution with n minus 2 degrees of freedom. And notice that the degrees of freedom here is n minus the number of parameters you needed to estimate in order to compute that statistic. In this case, you needed to compute both the intercept and the slope parameters to be able to determine these t-ratios, as they're called. Now, before we talk about the details of hypothesis testing, economics claims to be a science, and as a science, we try to use a scientific method. And when you're practicing this, you observe something in the world that you'd like to explain. And once you've observed this, you try to come up with some explanation for what's happening. And we call that a hypothesis. So you formulate a hypothesis, and then the next logical step is you test that hypothesis. There's only two possible outcomes for the test. Either your test results suggest that you're wrong, or you fail to reject. You only either reject or you fail to reject the hypothesis. Notice I didn't say you prove the hypothesis, because you can never prove that a hypothesis is correct. Instead, what we do is we specify some model that we think may work, and if we find that we're wrong, we reject it and we start over again. If, on the other hand, we get results consistent with our hypothesis, then we try to test it in other examples or other data sets to see how generally applicable our hypothesis seems to be. And we never claim to prove any result under the scientific method. It's part of what we call the philosophy of logical positivism, which has served the scientific community for a few centuries now. So basically, you can only falsify things. You can never prove something is correct. Because while your model may work in the test that you devised, it may fail in some tests that someone does next week. or next year or in another century. And a lot of things that scientists initially hypothesized held up for a long time until there was some new way of testing it or some new circumstances. And that's how progress is made, where hypotheses that seem to work break down, and then you have to come up with a better explanation that handles the new experiments, that takes into account the new information.